So good day everyone. Thank you all for joining. I hope you find the session insightful. If you have any questions in between the session, feel free to unmute yourself and ask anywhere between, or you can put your questions in the chat box, and towards the end I'll answer all those questions to the best of my knowledge. So let's start. So, introducing myself, I am Della Dominic. I am a recent computer science and engineering graduate of Rajgiri School of Engineering and Technology, and I will be joining Accenture India as an application developer next month. And this session is about MRI to CT cross modality image synthesis using a generative adversarial network architecture known as CycleGAN. Firstly, we will see what is generative adversarial network, also known as GAN, and what are its applications. And moving forward, we will see how we can translate MRI to a CT image using image-to-image translation application of GAN, and wherein we will see specifically the working of an architecture, GAN architecture known as CycleGAN. And after we go through all the steps involved in MRI to CT image translation process, we will end the session concluding with the limitations of the project and the future scope that is involved. Now, just to give a disclaimer, this is not a hands-on session. However, all the links to the code and the dataset will be included in the slides, and the slides will be shared after the session. So let's start. So what is generative adversarial network? Generative adversarial networks are deep learning networks that are used to generate a new data. The data can be image, it can be a text, or it can even be music, and hence the term generative in generative adversarial networks. It was first introduced in the year 2014 by Ian Goodfellow and his colleagues, and the term adversarial in generative adversarial networks means conflicting, and it is because of the conflicting operation between the two main components in a generative adversarial network, that is, the generator and the discriminator, both of which are neural network, hence the term network in generative adversarial network. The generator will try to generate whatever the GAN is supposed to generate. For example, in host to zebra translation, as you can see in the image, the target domain is zebra images, and the generator will try to generate zebra images. And the discriminator, which is a deep neural network, is essentially a classifier that will classify the generated images as fake or real. So both the generator and discriminator will try to conflict or try to outperform one another, and which is the basic principle behind generative adversarial network. In the next slide, that is here, now we will see the detailed working of these two components, that is the generator and the discriminator. The generator, which is a deep neural network, will be fed or will be trained with noise. Noise here in this application of host to zebra translation will be a set of images of host, and the generator will try to translate that host image into a zebra image. And initially in the training phase, the zebra images generated during the training will be really bad, and how it improves is dependent on the discriminator. What does the discriminator do? Discriminator is trained on real data. Here the real data means the real zebra images, and it will try to distinguish or discriminate, or it will basically classify the generated fake zebra images as fake or real. And the feedback that is obtained will be back propagated to both the generator and the discriminator, which will help in improving both the models. So as time progresses, what happens is the generator will become more improved in generating realistic zebra images, and the discriminator will get better at discriminating or classifying the real and fake zebra images. And ultimately, when the generator outperforms discriminator, that is, when the generator fools the discriminator, that is, when the generator generates images, zebra images, that the discriminator fails to recognize as fake, the training stops. And that's the basic principle I'm working behind generative adversarial network. Now, listed here are a few of the applications of the many applications of GAN. GAN can generate cartoon images, cartoon characters, and it can also generate realistic photographs. I don't know if you've heard of the site known as thispersondoesnotexist.com, which actually uses GAN to generate a non-existent person's photograph each time we refresh the page. And it's really wonderful how it works. You can actually, if you're interested, you can go over to the site thispersondoesnotexist.com and try out yourself. Coming back to the applications of GAN, other applications include text to image translation, generation of new human voices, photos to emojis translation, face aging applications, which most of you are really familiar with, at least might have used an application that creates aged images of yourself. Super resolution, that is converting low resolution images to high resolution images. Photo in painting, that is translating actual photographs to paintings. Clothing translation, video prediction, that is predicting the next frame of the video. And image to image translation, that is converting one image to another image translation, just as we saw in the case of horse to zebra translation. Few other examples of image to image translation are labels to street scene, labels to facade. As you can see, labels are provided and the facade of the actual image is generated. Also, black and white to color image is another example for image to image translation. Similarly, aerial to map image translation, day to night, edges to photo, etc. There are actually a lot. You can translate between apples and oranges, and also translate summer photographs to winter photographs, etc. But here in the session, we will be discussing, or we will be dealing with how we can translate MRI images to CT image, corresponding CT image using image to image synthesis application of a GAN architecture. Now, this was actually a final year project that I had done, and the main objectives of this particular project are obtaining realistic and synthetic CT images from the MRI images. Now, the need for this particular application, the specific applications, due to the fact that CT, that is which involves a lot of X-ray images to be taken from different angles, involves a lot of radiation in the process, and it can create harm to people, especially like pregnant women and infants. And there are, in such cases, incurring an actual CT scan is impractical. Uh, and such cases, depending on this model, is the only method. And for that, and for other reasons, like for example, when both these modalities are required for diagnostic purposes, in order to save extra cost and time, by preventing the need for taking actual CT scans, we can rely on this MRI to CT synthesis model. These are the main objectives of the project. Now, given here is an image of an MRI brain image and its corresponding CT brain image. MRI stands for magnetic resonance imaging and CT stands for computed tomography. MRI is mainly used for producing detailed and sharper images of soft tissues of our body parts. And due to the fact that calcium does not emit a signal for MRI, bony structures, including bone matters, are not reflected that much. They appear dark or black in color. As against that, in case of CT image will give detailed imaging of bony structures. It will be lighter or brighter in color, as against soft tissues, which will not be much detailed, and they will be either light gray in color or dark in color. Now, when it comes to a translation process or a translation application, like for example, MRI to CT or host to zebra, an important thing to notice the type of image that is involved in the data set. Image can be either paired or unpaired. For example, here in this case, this is an example of a paired image. We have an MRI brain image and corresponding CT image of the same patient of the same organ is present. So this is a paired image. So the data set can either be of paired images and unpaired images. And depending upon the application, paired images may or may not be available. For example, in the case of, as you can see, label to facade translation application, paired images can be obtained abundantly. Whereas in case of zebra to horse translation, corresponding there is no such thing as corresponding zebra image, right? We can only give a set of zebra images and a set of horse images. So in cases where unpaired images are less, paired images are less, or no, incurring paired images is not a possibility, we go for special kinds of GAN architectures like CycleGAN, DiscoGAN, DualGAN, etc. And for paired images, we have other different types of GAN architectures like pix-to-pix GAN. Here in this application, both paired and unpaired images are obtained, but abundantly we will get MRI and CT unpaired images, and hence I went for CycleGAN implementation of MRI to CT image translation, and we will discuss that in details. This is the symbols are three images from the MRI images and the CT images that we collected as part of the project. As you can see, axial images are collected. Axial means the section plane will be parallel to the plane. It is not longitudinal, it's parallel to the surface. Now, we will see in detail the architecture and the working of CycleGAN. Now, CycleGAN is basically an extension of GAN architecture or a type of GAN architecture, and it contains, main feature is that it contains two generator models and two discriminator models. One generator model will translate an image from domain A to the target domain B, and the other generator model will perform the operation in vice versa fashion. Here, in this case of MRI to CT translation, the first generator will translate MRI to CT, and the second generator is for translating CT images to MRI. A reason will be discussed in detail in the next slide. And corresponding to each generator model, we have a discriminator model for classifying whether the generated MRI or generated CT image is fake or real. Now, given here is two images. Basically, there are two cycles involved in the CycleGAN process. Concentrating on the left side of the image, as you can see, there are two generators, generator A to B and generator B to A. Consider A as the domain of input A, that is domain of MRI images, and B as a CT image. So generator A to B is essentially translate an MRI image to a CT image. In the first cycle, we are feeding MRI images to the generator, which will try to translate it into CT images. And the CT image is then given, generated CT image, which is the fake CT image, is given back to generate the second generator, that is generator B to A, that is CT to MRI translator generator, which will generate the reconstructed MRI image. So, and both these images, generated image and the reconstructed images, are tested or discriminated by the two discriminators as real or fake. That is, the generated CT image is discriminated or classified by the discriminator B, which is trained on real CT images, and the reconstructed MRI images are classified as real or fake by the discriminator A or the discriminator MRI, discriminator for the MRI, and that is trained on real MRI images. This is the forward cycle, and the cycle consistency laws between the reconstructed and the actual MRI images is used for improving both the generator and the discriminators. Now, this is the backward cycle wherein the same generators and the discriminators are used, only difference being that here initially CT images are fed to the first generator to generate MRI images, and from the generated fake MRI image, CT images are reconstructed. Initial CT images are reconstructed, and herein we obtain the backward cycle consistency laws. Now, this cycle consistency laws of is really important, especially, and that is one of the main advantages of CycleGAN. And this is important because we are using unpaired images. And both these cycle consistency laws and adversarial laws, that is the conflicting laws between the generator and discriminators, used to train the model further and improve the model. The brief architecture of the project. The different steps involved in the project are data acquisition, where data is collected, and secondly, data pre-processing and preparation, which is not a compulsory, to be honest, which is not a compulsory step in case of unpaired data. But if it was paired data, there's a step called co-registration, wherein we have to align both the images, since we are comparing pixel to pixel images of corresponding. Since you're using MRI and the corresponding CT, we have to compare the pixel to pixel. We're actually comparing the pixel to pixel intensities. So for that case, we need to align both the images, and co-registration is a very complex pre-processing step that needs to be done for paired images. For unpaired images, basically I used two main noise filtration method and N4 bias field correction method, which we will see later in detail. Third step is implementation of the CycleGAN model, and finally we have evaluation and fine tuning of the model and deployment of the model into a web app or a mobile app. First step, moving over to the first step, which is collection of the medical image from the data set. Actually, different data sets are available. We have the RIAR data set, but the amount of data in the RIAR data set is very limited. Hence, when I went for the project, I went for Cancer Imaging Archive. which actually has 12,000 plus images of MRI CT images of different organs. And from that 12,000 plus images, brain images were collected. In total, 1,408 MR brain images were collected and 864 CT brain images were collected. Out of these images, 300 axial images were collected because um, sorry, 300 axial images is collected because uniformity of the data set largely affects the training of the generator and the discriminator model. Hence, it is important that images are of the same section type as well as defects. Images with larger defects was avoided. Both the images, both MRI and CT images had a dimension of 256 into 256, and initially they were of the format DICOM format, which is the typical and most usually commonly found medical image formats. That was converted to NIFTY format, which is another format commonly used for medical imaging. Another reason for using NIFTY image was NIFTY format. Converting DICOM to images from DICOM format to NIFTY format was the fact that pre-processing and further processing is more simplified in case of NIFTY format. And the conversion from DICOM to NIFTY was done using a free software known as DCM to NII. Now, NIFTY images cannot be viewed directly like PNG or other images. For that, for viewing purpose, we used the software known as MRI cron, and both these images were added to different folders for further processing. First data pre-processing step that we used and employed was denoising using medium filter processing. As the name suggests, it is a task for removing noise from an image, and medium filter was used especially to remove impulse noise, that is salt and pepper noise, and it works by the fact that image pixels, we will move the filter mask is moved through the image pixel by pixel and replacing each value with the median value of the neighboring pixels, and this will avoid noises, especially salt and pepper noise. The reason why these noises are present in the MRI and CT images is because of the scanner's defect, MRI scanning machines and CT scanning machines defects. This is a sample example before and after image of denoising an MR brain image. Only a mild denoising is employed because over denoising the image might result in smoothing out the edges and thereby um, creates more unwanted results. This is an example. This is an image of CT images before and after denoising. The second step and the last pre-processing step that was used was N4 bias field correction, which is a popular method for correcting low frequency non-uniformity present in medical images, especially in the MRI modality of the image. And for that, we use the simple ITK Python package, which provides N4 bias field correction image filter. And using that, we perform the N4 bias field correction. And here is the before and after images of N4 bias field correction in MRI brain images. And this is N4 bias field correction used in CT brain images. This is the entire sequence of data pre-processing, original MRI image. Firstly, after denoising, we have an intermediate image on which N4 bias field correction was applied. Similarly, on CT brain image. Now coming to the most important part, model implementation and training. Number of epochs used. We actually employed a k-fold cross-validation method. For each fold, the number of epochs was 60 epochs, and the model optimizer used was Adam, and the learning rate was taken to be 0.0002, and the activation function was leaky relu. As mentioned earlier, loss functions involved are the forward cycle loss, backward cycle loss, and adversarial loss. Now, additionally, an identity loss was also taken, which is essentially obtained by feeding the generator with the target domain image. Here, in this case, the generator was inputted with CT images to generate CT images. This was essentially to understand that the image preserves the essential features of a CT image. Now, novelty of this approach, as against what was suggested in the original CycleGAN paper, is the use of optional identity loss for identity mapping, and going forward with a k-fold cross-validation approach. It was taken in order to reduce overfitting and also to validate our results. We used three folds by taking k value as 3. Given here is a summary of the training process that we actually did. K4 cross validation was performed with 3 splits, and the data set was split into 3 folds. The first fold containing 70% of the data, second fold containing 30% of the data, and the third fold containing 17% of the data. And in the first fold training, first fold 1 was taken, that is 70% of the data was taken as a training testing set, and the other two folds combined together formed the training set. And similarly, a similar approach was taken for the other two splits. For each fold, model was trained for 60 epochs, and training for each fold took approximately 6 hours. So in total, it took around 18 hours. Now, after each epoch, 5 random images from the training data and their corresponding translated CT images are saved as a single PNG file. And after every 5 such epochs, the trained model was saved in the format of .h5 format. Now, after training with 60 epochs, 60 output input file images and 12 trained models were saved. Here is a data sample of the first epoch. The first row depicts 5 random MRI images taken from the training dataset after first epoch, and second row, that is the last row, represents the corresponding CT images. As you can see, the translation is really poor, but as epochs progresses, as training progresses, you can see the difference in the translation. Even after just 50 epochs passed, the generated CT images looks much different from that what was obtained in epoch 1. After 60th epoch, these are the final result for the fold 1 model. After training and saving the model saved after the 60th epoch was loaded and tested against 3 evaluation matrices. Generally, 3 types of images were created. That is a real MRI image, the translated CT image was generated, and the reconstructed MRI image was generated. The reconstructed MRI image was generated because to compare the real and the reconstructed image. Since we are using unpaired images, we do not have a CT image to compare, a ground truth for the CT image to compare our results to. Hence, we are generating reconstructed images using the other generator, that is B2A generator, and comparing the real MRI and the reconstructed MRI. And the 3 models are evaluated against 3 evaluation metrics, namely structural similarity index, SSIM, mean squared error, MSE, PSNR, that is peak signal to noise ratio. SSIM, as the name suggests, structural similarity, it will compare the similarity in structure of the 2 images. Here, the MRI, the real MRI and the reconstructed MRI image. So the higher SSIM value means a more closer image than the original, with 1 being the same. 1 will not be obtained, definitely something closer to 1, like 0.9 is, with something between 0.8 and 0.9 is considered to be a good translation. And it is expressed by the following equation. Mu represents the mean and sigma represents the variance, and Cn and C2 are constants. The second evaluation metric used was peak signal to noise ratio. PSNR is mostly used as a quality measurement between 2 images, just like SSIM, and it represents a measure of the peak error. The higher the PSNR value, it will be better. So it is computed using max, that is maximum intensity value of the image, and MSE, that is mean squared error, which is essentially the third and final evaluation metric, mean squared error. Mean squared error is commonly used metric for any reconstruction problem, and we take the square of the difference between every pixel in the source and the target image. Here, in the case, it will be the real image, real MRI, and the reconstructed MRI image. And then we will sum up that and divide it by the number of pixels represented by n. Unlike the other 2 values, for a better translation, we require a lower MSE value. These are the final results, that is the SSIM, PSN, and MSE values of all the 3 folds, or all the 3 splits involved. And as you can see, taking SSIM as the primary evaluation metric, we find that fold 1 was more comparatively better than the other 2 folds. These are the results of SSIM, PSN, and MSE values, graphical representation of the same. And here are a sample, just a few sample output of the final output result of fold 1 model, of fold 1 split. Here as you can see, SSIM ranges between 0.7 to 0.8. We have the input MRI, the generated CT of the corresponding MRI, and the reconstructed MRI. These are 10 samples, and these are the quantitative results obtained for these 10 samples that are taken. And as you can see, average SSIM accounts to be about 0.772, PSNR about 36, and MSC is about 31.6. Graphical representation of the results. This is the SSIM of all the 10 samples. As said earlier, a higher SSIM value is preferred and average is around high value. Similarly, PSNR is also a high value for all the 10 samples, and comparatively, MSC value is lower, and except for a few data points. Summing up the entire results obtained, the average score obtained from the training the model using 3-4 cross validation with 300 samples is given as below. That is, average SSIM is 0.81, average PSNR score is 33.16, and MSC is 31.56. Both these models took approximately 6 hours each to finish their training. Now, even though it translates the MRI to CT image, it does definitely have a lot of limitations. The main limitation is the generated CT image does not represent the exact translation. And when it comes to something crucial of an application like something in a medical field, relying on this model that has just a structural similarity of 0.7 to 0.8 is not a final solution. Therefore, it does have limitations, and there is provision for improving more on the model to generate realistic, more exact corresponding CT images, the MRI images. Now, another major defect is not maintaining major artifact. If the MRI image that you have at hand has major artifacts or major defects in terms of noise or any other poor performance, poor representation in terms of intensity or whatsoever, the translation, no matter how much better the model will be, the translation, the end result will be poor. And then another important thing is structural consistency. It cannot guarantee structural consistency, and that again is the reason why we are using axial images to train the model, and the model will only work on axial brain images. It will not give a similar result for coronal or sagittal sections, that is longitudinal sections of the brain or any other part of the organ, and this is because of structural consistency. Now, last and yet again another important limitation is the lack of a proper metric to evaluate how much accurate the generated CT is. One reason is the fact that we're using unpaired images. So relying completely on MRI and reconstructed image comparison is not completely, a right method and right metrics. These three metrics are not the exact metrics and doesn't give full information on how much correct translation is happening there. And that brings us to the future scope of the project. So these limitations, we can actually build upon these limitations and further improve the model in different ways. First one is incorporating some measure in the form of a loss or another parameter to ensure structural similarity. Also, the model can be improved by improving the data set. The data we used was around 300 data set, but instead using more uniform data, even if it's less in number, yields more accurate results from as per research papers. Now, for example, the MRI data sets that we collected consisted of different contrast. We have T1 weighted contrast of MRI image, T2 weighted contrast of MRI image. So there was a lot of non-uniformity in the data set that involved that also affected the performance of the model. So using a more uniform data set will improve the model, and also incorporating 3D images, that is different slices, voxel images, different slices of MRI images can also improve the model to a large extent. With that, we have come to the end of the session. I've also provided links to the code as well as data set. You can go ahead and look that when I share the slide later on. If you have any questions, feel free to unmute yourself and ask, or else you can put your questions in the chat box. Um, Thanks, Udaya. I don't know if you have pronounced your name rightly, but thank you. Is there any questions? And thank you again for joining. Thank you, Harini. We used it was trained on Kaggle. Thank you, John. Okay, I guess we don't have any questions. That will be end of it. Thank you, everyone. Thank you for joining.